All right, significant figures and calculations using those significant figures. So, a little bit of review hopefully here. If you've ever learned about scientific notation, you already know some of this stuff. So, there will be a link to a Wikipedia page that summarizes it in quite a bit more detail with a lot more examples, but for right now, what you need to know, a zero, and the most important thing to know about, or rather, how do I put this? Yeah, zeros are the only thing that really could possibly be not significant. So let's just focus on the zeros. Well, let's start with when they are. Zeros are significant if they are between two other numbers that are non-zero. Write an example of that. So if you see something like 102, that zero is a significant figure, and this would have a total of 3 significant figures. Now if you had something like 10,000.1, all 3 of those zeros in between are significant, so you would have a total of 5 significant figures. Okay. Zeros are not significant if they follow a number with no decimal involved, and they're also not significant if they lead a number after a decimal with no other numbers in front of them. And so this is the trailing zeros are not significant, leading zeros are not significant rules that you may remember from learning about significant figures and how to turn things into scientific notation. Let's give these letters or something, A and B. So A will be examples of zeros are not significant if they follow a number with no decimal. B's will be zeros are also not significant if they lead a number after a decimal with no other numbers in front of them. Examples of type A. The number 100 has one significant figure. 100 point would have 3 significant figures because there is a decimal involved. 100.0 would have 4 significant figures. So the trailing zero thing is sort of if you don't have a decimal point and there's just a number followed by a bunch of zeros, only that number is really treated as significant. Let's see. Other examples would be something like if you had a number 1040, that has 3 digits of precision. The final trailing zero is not significant. The one buried between 2 numbers is significant. Okay, examples of the B type. If you have something like 0.001, that has 1 digit of precision. Those are leading zeros with nothing in front of them. Okay, if you have 0.0204, that's going to have 3 digits of precision. The leading 0.0 is not significant. It doesn't give you digits of value. Okay, I hope that's enough examples. You've got the idea what's going on because we immediately get into application. So, why does all of this matter? Well, primarily for multiplication and division. Although it's also going to play into what goes on when we have addition and subtraction. But when you multiply or divide 2 numbers, you're only able to keep as much precision, in other words, significant figures, as the less precise number, or the one with fewer significant figures. Okay, So as an example, if you were doing something like 102 times 10, well, that's not going to be very precise because you have 3 digits of precision and 1 digit of precision. So once you multiply this, you would say, let me see, it would precisely be 1020, but we would need to round it to 1000 because we only have 1 digit of claimed precision that we can have at the end. It can get to be kind of a trial. The same thing happens with division. You'd have to look at the rules and you have to keep the fewest number of sig figs, whichever way it goes. All right. How does it deal with addition and subtraction? Well, there it's less about the number of significant figures, but you must keep the less well-known number, or less well-known place value. So in the case of addition and subtraction, you're actually looking at place values that are significant. Oops. Okay, let's see. So, simple example. If you had something like 1.01 plus 0.007, the first number is only known to the hundredths place, the second one is known to the thousandths. If you added them in the normal manner, you'd get 1.017. But because of the rule that you must keep the lesser digits of precision, or the lesser place value, less well-known place value, we have to truncate that to the tenths place. In this case, that will mean rounding up to 1.02. Same kind of thing can happen as with the multiplication, where you can lose a tremendous amount of precision. So yeah, be careful with these kinds of things. All right, I think that's about all I want to say about these. So we're going to stop here. There will be a practice problem we'll be trying shortly, and it'll be a little bit more interesting than these were. So see you in that video.